Hello, this is Song Park, an undergraduate research assistant at the TM Lab. Today, I am introducing a paper titled A doc2vec and Local Outlier Factor Approach to the Measuring of Novelty of Patents. The table of contents is listed above. This paper was published in Technological Forecasting in Social Change, a Q1 journal. A keyword includes patent analysis, patent novelty, doc2vec, and local outlier factor. I wrote this paper to share because it introduces a new approaches to measuring the value of patents, moving beyond traditional quantitative indicators. Now let's begin with the introduction. There have been several approaches to measuring the novelty of patents, which can be categorized into three main methods. First, patent backward citation analysis measure novelty by counting the number of backward citation or analyzing the relationship between a patent and prior inventions. This idea behind this approach is that the fewer citations a patent has, the more novel it is. Second, patent classification analysis evaluates novelty by comparing the classification codes of a patent with those of prior patents. Lastly, patent text analysis uses text matching techniques such as keyword analysis and SEO analysis to extract and analyze the technological content of patents. This approach allows the researchers to assess novelty based on actual textual information in patents rather than just citation data or classification codes. While these approaches are effective or measuring similarity in generating patent maps, they have some limitations. They require substantial time and cost due to the need for domain-specific knowledge. This means that expert intervention is often necessary to refine and interpret these results, making this method less efficient and scalable. This study introduces a machine learning approach to measuring patent novelty. It combines a neural network-based document embedding technique, doc2vec, with a density-based anomaly detection method called the local outlier factor or LOF. Then why did the researchers choose doc2vec? There are two key reasons. First, it has been proven to be valid and reliable for generating patent vectors. Second, it strikes a good balance between time complexity and computational efficiency, making it practical for large-scale patent analysis. And also, LOF was selected because it's capable of detecting local outliers even when the data is unevenly distributed or contains inconsistent patterns. Plus, it has already been successfully applied in previous studies on measuring patent novelty. Here's the background. Here's the research framework. This approach consists of three main stages. First is patent collection. Patents are gathered from the USPTO database and only patent claims are used since they describe the technical and legal scope of the invention. The text is then pre-processed by removing stop words, special characters, and numbers. Second is patent embedding. The clean patent claims are input into the doc2vec PVDM model, which patents with the similar technical descriptions are placed closer together in the vector space. Third is novelty scoring. The LOF is used to assign a numerical novelty score, identifying patents that stands out from the rest. Finally, to validate this approach, a comparative analysis is conducted using correlation and forward citation analysis to assess the impact of novel patents. This slide is to explain the difference between PVDM and PVDBOW of doc2vec. Since PVDM is adopted in this research, so to explain the details, this model extends the CBOW approaches to learn document vectors as well. In doc2vec, PVDM predicts the target word using both context words and the document vector. This allows it to generate meaningful document embeddings. When patent documents are converted into vectors, patents with similar technologies are positioned closer together in the vector space. Meanwhile, patents are far from othered in the space may be considered as the patents with new or novel technologies. Now let's talk about the LOF. This is a density-based outlier detection method used to measure patent novelty. If a patent is similar to its neighboring patents, its LOF value is small, close to 1, meaning it aligns with existing technologies. On the other hand, if a patent significantly differs from its neighbors, the LOF value is greater than 1, indicating a high possibility of being a new technology. The calculation process involves several steps. First, indicating the k-nearest neighbors for each patent, then grouping these neighbors and calculating the reachability distance. Next, computing the local reachability density, and finally deriving the LOF value. As shown in the diagram, patents surrounded by many similar patents have LOF values close to 1, while more isolated patents have higher LOF values, signaling novelty. Now let's move on to empirical analysis and results. For the empirical analysis, medical imaging technology was selected as the case study. To validate this approach, 2 analyses were conducted. First one is a correlation analysis comparing the novelty scores with previous novelty indicators. Second one is a comparative analysis examining the technological impact of novel patents using 4 citations. Now let's move on to step 1. Step 1 is a data collection and pre-processing. A total of 1877 medical imaging patents filed from the USPTO database using keywords queries such as above. For natural language processing, the Genzim library and pre-processed string model were used to clean the patent text. This involved removing special characters, numbers, and stop words like the and but. Additionally, verb stemming was applied, such as converting words like image and imaging into image, IMAG, for consistency. In step 2, a patent vector space model was constructed using the doc2vec model in Genzim. With DM set to 1, they could set PVDM. The model incorporated patent claims and patent numbers as inputs to learn document vectors by predicting target words. For parameter settings, the window size, which determines the number of words considered as input, was set to 5. The number of epochs was set to 50 for effective training. Previous research has shown that increasing the dimensionality of word embeddings beyond 300 does not significantly improve quality. So 3 experiments were conducted with vector dimensions of 64, 128, and 256. In the end, the vector space model with a dimension of 256 was selected. In step 3, the novelty of patents was calculated using LOF, which was implemented with the local outlier factor model from the Python-based scikit-learn library. The LOF hyperparameter k is set to 20. if the hyperparameter value is large, the number of neighbors considered for calculating the local density increases, meaning the novelty of a patent is judged over a wider range. On the other hand, if the hyperparameter value is small, the local density is calculated within a narrower range, providing a more fine-grained assessment of novelty. After computing LOF, some patents were identified as novel patents. For validation, a correlation analysis was conducted using 3 patent indicators: originality, radicalness, and reverse radicalness. Originality measures how diverse technologies has been synthesized in a patent based on backward citations. Patents with more diverse classification codes among their references are assigned higher originality scores. Radicalness is another citation-based indicator that measure how much new technological knowledge is adopted in a patent. It is calculated by counting the classification codes in referenced patents that do not appear in a focal patent. Reverse radicalness, on the other hand, is derived from radicalness but focuses on the number of classification codes assigned to a focal patent but not to its reference patents. Since it directly measures the amount of new technological knowledge created by patents, it has a stronger connection with novelty score, which is suggested in this paper. Here's a table summarizing the 3 indicators mentioned just before. To analyze the technological impact of patents, the number of forward citations received within 7 years of issuance was used as an indicator. This analysis focused on a patent filed up to 2013. To ensure reliability, it only considers data from 1999 onward, when at least 100 patents were filed annually in the medical imaging field. The novelty of patents were measured. In the top of 10%, classified as novel patents, were compared against the remaining 90%. Now let's discuss the issues with the existing novelty measurement method. Novelty patents receive, on average, twice as many forward citations as other patents. However, the variance in forward citations is high, meaning that while some patents have a significant technological impact, but others do not. This suggests that a simple novelty score alone is insufficient to fully explain technological impact. To address these limitations, new novelty indicators, originality and radicalness, were introduced for analysis. These new indicators were calculated for 820 patents filed up to 2013, and Z-score normalization was applied to improve interpretability. Now this is a discussion session. To conclude, this approach does not replace traditional classification and citation-based method, but rather complements them. While existing methods evaluate novelty by analyzing classification codes and backward citations, this method leverages patent text to distinguish subtle differences within the same technological category. This allows for a more precise assessment of technological novelty. Another key advantage is that this method eliminates the need for domain-specific knowledge in keyword extraction, making it possible to search for novelty patents across various fields more efficiently. And since the approach utilizes patent text from early stages, it can reduce the time required for technology forecasting. And by using the doc2vec technique, it is possible to analyze not only patents but also other data like academic papers or other sources. And now, here's the conclusions. To summarize, this study developed a machine learning model measure the novelty of patents without relying on domain-specific knowledge. By combining doc2vec and LOF, this approach identifies new patents in fully automated manner and can be utilized regardless of the technological sector. If a system is developed to automate this approach, it can assist individuals in identifying novel patents. Furthermore, it can be beneficial for small and medium-sized enterprises in identifying technological opportunities. There are several limitations to consider in this study. First, while the proposed approach effectively identifies novel patents, but it does not necessarily mean that these patents represent groundbreaking inventions with significant technological or commercial impact. Another limitation is related to the model itself. While doc2vec was used to construct the patent vector space, it is not only the available method. The approach could be further refined by incorporating more advanced NLP techniques to improve accuracy and reliability. Additionally, the result of novelty detection may depend on the choice of hyperparameters for doc2vec and LOF. In this study, hyperparameters were set based on pilot test results, but introducing systematic tuning method could enhance the robustness of the approach. Finally, this study was conducted as a single case study within the field of medical imaging technology. So these are limitations. This is end of my paper review. Thank you for listening.